So in this section, we're going to look at the phenomenon of built-in potentials. And these can arise anywhere that there's a difference in the doping as a function of distance. So let's talk about a situation first that occurs in standard semiconductor processing. So we have our silicon wafer here, and let's imagine for a moment that it's simply intrinsic, although we could also make it doped p-type or n-type at a certain level, and it wouldn't change the phenomenology. So we'll plot on this axis the number of donors per centimeter cubed versus distance. Now, ion implantation is a common process in semiconductor fabrication, and it literally shoots dopant atoms into the material. And what results is a concentration profile that looks something like this versus distance. So now our ND is a function of x. So what are the consequences of this? Well, first thing, let's remember that in our simple approximation, our n is approximately equal to nd. And then let's remember that n is approximately nc exponential to the minus ec minus ef over kBt. And this is, I'm saying approximate because we're using the Boltzmann approximation here. So if we rearrange this equation, what we can see is that nd over nc negative kBt log this is equal to this energy distance EC minus EF. So let's draw this quickly here. EF, EC, and we're talking about this energy distance here. Now, we can also measure the energy distance between EF and the intrinsic Fermi energy. And this energy distance we can define as E times the electric potential phi here. So we can also express this equation slightly different way. Instead of writing it in terms of NC, we could say negative kBt times log of so this energy difference here is E times our electric potential phi. So now we need to see what happens if we have a changing number of dopants versus distance. Well, what's going to happen is if we make this a function of x, the Fermi level has to remain constant because we're talking about a situation of thermal equilibrium. So throughout the entire semiconductor wafer, the Fermi level must be constant. So it's the intrinsic Fermi level that and the voltage which have to change versus distance. So let's take a look at what this looks like. So let's go back now to our example of an ion-implanted semiconductor. So we're plotting the log of the number of donors versus the distance, x. And the implanted profile looks something like this, ND of X. Now realistically, the wafer will have some background doping. Let's call this Na. So the net charge density would be Na minus Nd here, Nd of X here, and on this side it will be Nd of X minus Na. This is the net charge density. Now, going back to our carrier number equations, we can determine the potential in both of these areas. So our N of X is going to equal Ni exponential to the EF minus EI over KBT. And we can substitute in here for E phi of X. Now what does that mean on this diagram here? So what I'm actually doing is I'm going to determine this field as a function of distance and then superimpose that on the band diagram. So instead of having a flat conduction band versus distance, the presence of this non-uniform impurity distribution actually introduces some band bending or some curves in the band diagram. So very far away from this impurity profile, deep in the wafer, I'm going to draw first my band diagram. So I know that there's more acceptors than donors, and so out here my Fermi level has to be closer to the valence band edge. And of course, here's our band gap. So then let's look at this position at the peak here. So at the peak of this distribution of donors, what's going to happen is the Fermi level has to be closer to the conduction band edge. So I'm just going to draw a little section of semiconductor here to represent this region. And this is the same E gap. And then we have to have equal positions of the conduction band edge at these two positions, so approximately at the surface and approximately here. Now if I connect these regions with curved lines, the overall band diagram has to look something like this. And we'll learn later a little more about the details of the shapes of these lines when we start talking about PN junctions and Schottky junctions. So the presence of this non-uniform impurity distribution actually introduces this band bending in the semiconductor. And for completeness, we should revisit this idea of where E sub I is, and then talk about the built-in potential. So E sub I is always approximately in the middle of the band gap for especially silicon, and it slightly deviates based on the effective densities of states. And our potential is then measured as the distance between these. So this is E phi here and E phi here. So the difference in potential would be known as our built-in potential. And so a total voltage difference, and this is really a pseudo voltage internal to the material, not an externally applied voltage, occurs between these 2 points. So if we take this as our reference, we could calculate how many volts equivalent the presence of those dopants have induced inside the semiconductor. So in this short section, we've looked at how a non-uniform distribution of dopants or carriers inside a semiconductor results in built-in voltages and band bending. And it's these differences in Fermi level position and this built-in voltage which allows us to construct devices out of semiconductors in the first place. So we'll return to this theme again and again throughout the course when we investigate p-n junctions and transistors and other types of devices. It's always important to remember that the difference between the Fermi energy and some reference energy is intimately related to the density of carriers at that local point. And we can choose either a conduction band or valence band edge or the intrinsic, the position of the intrinsic Fermi level as our reference energy.